Hi friends, in this term we will also learn modern analysis and the problems about modern analysis, modern mathematics. And the purpose of this term is to review some topics from our previous lessons, previous lectures, for example, from analysis, complex analysis, real analysis, also some topics from algebra and etc. Before starting the main topics, let's recall our sets and numbers and some theories about that. So, let's start. Introduction. A set is a concept so basic to modern mathematics that it's not possible to give it a precise definition without going deeply into the study of mathematical logic. What does it mean? It means that a set is a collection of objects. For example, some trees, a collection of trees, a collection of students, a collection of teachers, or a collection of flowers, and etc. Commonly, a set is described as any collection of objects, but no attempt is made to say what a collection is or what an object is. The object may be also numbers. The objects that together make up a particular set are called the elements or members of the set. Later in this term, we will be looking with some detail into the properties of certain sets of numbers. We are going to rely on your experience with numbers and not spend a great deal of time on the development of the real number system, okay? We assume that you know the real number system and its properties, but we just give a brief information about this. In particular, we assume familiarity with integers or whole numbers, such as negative 79, negative 3, 0, 12, and etc. The rational numbers, such as minus 5, 3, 11, 17, and etc., are expressible as a ratio of integers. Or those numbers which are not rational, called irrational numbers. And there was a noise outside, so I closed the window. Okay, and real numbers, which are numbers that are either rational numbers or irrational numbers. And the ordering of the real numbers using the inequalities sign less or greater, or less than or equal, greater than or equal. The representation of the real numbers as points along a line, and the option G, the fact in F here that the real numbers fill the line, leaving no holes to every point on the line. They correspond a real number. For example, let it be a line. Okay, this is 0. Let it be 1, let it be 2, and that is negative 1. You see, here is no holes. Every point, they corresponds a number to every point. For example, let it be 0.1, 0.1, or here is 0.99, or some irrational numbers maybe. It means that there is no hole between two whole numbers, okay? Let's continue. By way of review, we remark that we assume the ability to perform simple manipulations with inequalities. Manipulations means operations. In particular, the following should be known. If A and B are real numbers, any two real numbers, and A is less than B here, then minus A is greater than minus B, negative B. Or, for example, if A is 5 and B is 7, okay, you know 5 is less than 7, but minus 5 is greater than 7, minus 7, negative 7, or 1 over 5 is greater than 1 over 7, and etc. But here we have one premise: if A is greater than 0 and B is greater than less than 0. Okay, the square root of A and B is also the square root of A is also less than square root of B if also this condition is satisfied. So, what else we will learn in this chapter? The absolute value. What is the absolute value? We may define the absolute value in the model, okay, of any real numbers. Here is the model A is equal to square root of A squared. More commonly and equivalently, of course, we say that model A is equal to A whenever A is a positive number, and if A is negative number, model A is equal to negative A, okay? Here is if A is less than 0, A is negative, answer is minus A. For any real numbers A and B, we have the model of A plus B is less than model of A plus model of B. Also, the model of A times B is less than model of A times model of B. Let's give an example. Let it be 5 and let it be minus 2. 5 plus minus 2 is 3. Yes, this is 3. Let me write it like that. Okay. Model 5 is, 5 again, and model minus 2 is positive 2. You see, 3 is less than or equal to 5 plus 2. Okay, we proved this fact, and let's continue. Complex numbers. What about complex numbers? We learned the complex number in the previous term. I think you do not have any question about complex numbers, but if you have any question, please inform me, let me know, comment below. And we also assume a knowledge of complex numbers, numbers of the form A plus I times B. Here, E is an imaginary unit. This is I. This is an imaginary unit. A and B are real numbers. I square satisfies minus 1. Okay, if Z is equal to A plus I times B, if this is a complex number, then the real part is A here. This is real part, as I mentioned here, and B is imaginary part. I mentioned it here. The conjugate of any complex number is a minus I times b. And the model is the square root of the sum of the squares of real part and the imaginary part, of course, under the square root here. And let me write an example. For example, let z be 5 plus 5 is very good number. 3 times I, let it be. Okay. The real part is 5. This is real part. Okay. The imaginary part is 3. This is imaginary part. And the conjugate, we write it like that. Conjugate is 5 minus 3 times e. And the model is, the model z is equal to the square root of 5 square, 25, plus minus 3 square is 9. Yes, and this is equal to the square root of 34. Okay, I think it's obvious. If you have any unclear part, please let me inform. Let me now inform me. And let's continue. Properties of complex numbers. There's some properties. The conjugate of conjugate complex number is equal to itself. Okay, and here are some properties of the sum of conjugate complex numbers, the multiplication of, and the model of real z, imaginary z, and etc. I think this is a brief information, and I don't want to give a detailed information about that because we have learned these properties very deeply in our previous lectures. And let's just continue. Definition. The following symbols denote the stated sets. N, you know, is the set of all positive integers. Let it be just N, natural numbers, positive integers. Okay, Z is the set of all integers, positive, negative, and 0. It means that N, the set of positive integers, the natural number set, is included to Z. We can write it like that, okay? This is Z, and you see N is included to Z. Okay, let it be like that. Somehow. Okay, Q is the set of all rational numbers. It means that N, Z are included to Q. Let it be Q. Okay. R is real number set. And here is our R. Great. And R plus are set of all non-negative real numbers. Okay. Here, R plus is included to, I think, let it be R plus, or sometimes you can write it like that. R plus is equal to set of non-negative, set of positive numbers, okay? Just positive real numbers. Positive R, not negative. C is the set of all complex numbers, and we recalled complex numbers in previous chapter, in previous slide. And let's continue. Okay, ordered pairs. What are ordered pairs? An important aspect in the understanding of sets is that the order in which their elements are listed is irrelevant. What does it mean? For example, here we have three sets. 1, 2, 3, first set. 2, 1, just 3, 1, 2, and 2, 1, 3. Okay, three sets. They are these three sets all are the same set. Okay, but they are written in different ways. Okay, but however, on many occasions, we need to be able to specify the first position, the second position, and so on. And for this, we need a new notion. And we speak of ordered pairs of two elements, ordered triples of three elements, and generally, if we have n elements, we name it ordered intervals, okay, of n elements, with this property that each requires for its full determination a list of its elements and the order in which they are to be listed. The elements in their right order are enclosed in parentheses. Here we have ordered triples: 1, 2, 3, 3, 1, 2, and 3 and 2, 1, 3. See the difference? See the braces firstly. This is the brace of just a set, but this is the brace of ordered pairs. Okay, these three pairs are different ordered pairs. For example, let it be if we want to speak about three-dimensional system, let it be X, let it be Y, and this is Z. Okay, let me write it here. Z, okay, X, and Y. So our first element is 1. X is 1. Y is 2, and Z is 3. Okay, you see, if we want to, where is this? This point is, let it be here. Okay, but here, this in the second ordered pair, X is 3. Here, X is 2. You see, they are different ordered triples. Okay, can you imagine the difference between ordered pairs and just listed elements? And let's continue. A definition. A set S is called a subset of X, and this is denoted by this sign. If every element of S is also an element of X. Here the sign. S is a subset, the sign of subset. Two sets X and Y are called equal, and this is denoted by X is equal to Y if each is a subset of the others. If both X is a subset of Y and Y is a subset of X. Otherwise, we say that X is not equal to Y. So a set which is a subset of any other set is called null set or empty set. Null set has no elements, and this is denoted by this sign. And a set is called a proper subset of a set X if S is subset of X, but S is not equal to X. Let me write 1, 2. Okay, this is our set. Okay, let it be X. The subsets of X is 1. My brace is really awful. 2, and let it be something like that. Wait, sorry. 1, 2. These are the subsets of X. But what about proper subsets? Proper subsets are just 1 and 2, not 1, 2, okay? This condition is satisfied here. And the union of two sets, X and Y, denoted by X union Y, is the set of elements belonging to at least one of X and Y. Let's give some examples on these sets. Okay, let's do intersection of two sets X and Y denoted by X. Intersection B is the set of elements belonging to both X and Y. Okay, the Cartesian product. What about the Cartesian product of two sets? Is the set of all ordered pairs. This is different from intersection union. Okay, ordered pairs. The elements, the order of the elements matter. Okay, in this Cartesian product, the first element of which belong to X and the second element belong to Y. The complement of a set X denoted by this sign. Okay, this is the sign of complement, is the set of elements that do not belong to X. Okay, we can write it like Y minus X, the subtraction of two sets. Let's give some examples. Okay, we have two sets, 1, 3, 5 and 1, 4, X and Y. Okay, the union is 1, 3, 5. Here we have 1, 4. 1 is the same, just we add 4 here. Okay, 1, 3, 4, 5. The intersection is just 1 because the intersection is the element that included both to X and Y. This is just 1. The Cartesian product of xy. Please give attention to the order of sets. Here x is the first, here y is the first, okay? If x is first and y is the second set, the ordered pair is like that. 1, 1, then 1, 4, 3, 1, then 3, 4. Let me write it in different color. 5, 1, and 5, 4. Okay, they are the ordered pairs of Cartesian product x and y. What about finding the Cartesian product of y and x? You see, here we have 3, 1, but here we have 1, 3. This is different, okay, ordered pairs. Here we have 5, 1, 1, 5. You see, the Cartesian product of x, y is not equal to Cartesian product of y, x, actually. So the set y minus x, let me clear, y minus x is just 4. Okay, if we subtract, we remain just 4. Okay, I think it's clear, but if you have any unclear parts, please let me know. The definition of union, intersection, and Cartesian product of sets be extended to more than two sets. If we have n set, which are x1 into xn, the union or the intersection or the Cartesian products are defined as like that, with this sign, okay? The union of x k such that k is from 1 to n, or intersection or Cartesian product, if we have more than two sets. And what about the sum of elements? The notation in the middle are similar to the familiar sigma notation for addition. For example, if we have real numbers x1 to xn, the sum of these real numbers are denoted with this sign. And for Cartesian products only, there is a further simplification of notation when all the sets are equal. Okay, if we have n equal sets from x1 to xn, you see here, x1, xz, all sets are equal. Then in place of the Cartesian product, we can write like that, the Cartesian product of xk, or just the Cartesian product of x. We write simply x to the n. It means that we have n equal sets, are suggested by the cross product. Notation is cross product, this cross product, but not that there is no suggestion of multiplication. Xn is the set of n tuples, okay? In particular, it's common to write r to the n for the set of all n tuples. If we have two sets, we write r2. Or if we have triple, we write R3, okay? And also Cn for the all n tuples of complex numbers. And theorem. Let x, y, and z be sets. Then these laws are satisfied, okay? We learned it in our previous chapters. Let me recall you. The complement of x you see, the complement of complement x is equal to x itself. Wow, what did I do? Sorry. Okay, the complement of complement x is equal to itself. The union of x and y is equal to union of y and x. It means that also it's true for the intersection. It means that commutative rules are satisfied in union and intersection. The orders doesn't matter. The second, this is associative rule, okay? If we group them 2 by 2, it doesn't change the result, okay? And third law is the distributive law. This is familiar with the multiplication rule, okay? We just multiply, let me say, find the union of x with y, then intersection, and the union of x with z. And this is true for the intersection also. And Next slide. The theorem about null set. Okay, here we have three. Theorem is three options. Let me say it like that. All empty sets are equal. Yes, the set, if the set has no element, this is empty set. I have one empty set with no element, and I have second empty set with no element. You see, empty, and these are equal to each other. The empty set has no elements, and the only set with no element is the empty set. If two sets X and Y have no elements in common, okay, we wish to speak of their intersection. For example, let me give an example. If, wow, sorry. If we have set A, let it be A and B, the elements. And let we have B, the elements are C and D. You see, they have no common elements. And the intersection of these two sets are equal to null set, just empty set. Okay, these two sets are called disjoint sets. Disjoint means having no common element. And second part, these are some exercises about this topic, this lecture, this presentation. Also, we can say, please try to solve these exercises yourself. If you have any question, please let me know, commenting below. And that's all. See you in our next lesson. Goodbye.